Okay, so last lesson we looked at this really simple example where a golf ball is projected horizontally off a cliff with a velocity, initial velocity in the x direction of 20.0 meters per second, okay? And in this situation, things are really quite simple because, of course, we remember that we have an initial velocity in the y direction of 0 and an acceleration in the y direction of g. We're going to get more into that later on because we actually don't need that for this problem because we're simply given the time that this whole thing occurred. So if we want to know how fast something went horizontally and we know how fast it was going, that's just distance equals velocity times time, right? How fast was it going? How long was it going that fast for? How far did it make it? That's all this problem boils down to. For you to recognize that that's how simple this problem is, you do need to have an appreciation of what we're describing here and what's actually happening here. So it's important that we recognize that. But let's look at a trickier example where it is not quite so simple. It's not just velocity is distance is velocity times time, and it's actually going to use some of our formulas. Can you make sure that you have your formula and data book available to you right now? We're going to, again, be taking from the gravity and motion section, not just the linear motion and force. We're not doing linear motion now. We're doing two-dimensional motion and projectile motion. All right, the problem we're looking at today is work example 1.2D from your textbook. If anyone wanted to follow along. Our title for today's lesson is still going to be horizontal projection. We're going to do one more example from this topic before we move on to projection at an angle. Date today is the 18th of the 10th. So let's have a good read of this problem, hey? A rock is thrown horizontally at a speed of 35 meters per second off a cliff that is 75 meters high. Determine the impact velocity. Now they're referring to a vector velocity here. I want you all to draw a diagram that clearly indicates the known information about the time initially, so the start of the projectile motion, and the final time, because we are going to look at the impact velocity. So I want you to draw that diagram so it shows that final time, that impact velocity, and what would be happening there. I'll show you what I expect that to look like in a moment, but I'll give you guys 30 seconds to try and draw your own diagram of that. If you want to copy the question down as well, you're welcome to. An alternative is copy down the key information as known variables and use that correct notation, okay? So off to the side somewhere, you can say u as a vector, 35 meters per second. And there's something you should identify about this u. Won't say anymore. S, some sort of displacement is given. I won't say any more about that either. Find V. Now, this is going to be quite a large, complex problem, so there'll be a couple of things that we tick off on this, but I just want to jump straight to this, and then we'll get you guys to do some exercises where you can consolidate some of it, because a couple of new things will come up in this example. All right, I'm going to start my diagram now. Hopefully you're ahead of me and you finish well before me. cross. And hopefully you have something like that. I'm going to tidy up this impact point. Made a bit of a mess of that. Vector quantity v some final velocity. Okay, did everyone have something similar to that? Yeah, does anyone have any differences that they want to check are okay? Because there's some variations to this that are reasonable. No? Okay. Now there's one very important thing that I identified when I wrote my known information that I hope you guys do identify as well, and that's that the displacement we're given, y, is negative. Remember that displacement, unlike distance, displacement is a vector quantity. It has a direction, yeah? It's also not, a track of where you've traveled. That's distance, and that's not a physics concept that we look at very often. Displacement is just the difference in positions, some change in positions, okay? But it has a direction. Be here and here, your displacement has a direction. In this case, we've clearly indicated that direction using a negative number. Now, did I have to use a negative number? Could I do this problem with a positive number for displacement? Absolutely. If you're on the North Pole doing this rock throw, you go downwards. If you go to the South Pole, up is down, down is up. What is down? What is up? No one knows, no one cares. You pick, you tell me, okay? Whether you do this, positive, positive, or whatever you want to do, up is positive, you could say that in words, whatever. You need to establish a frame of reference. If you don't, you might make this mistake as well. Acceleration, in my example, is not 9.8 meters per second squared. What is it? Negative. And this is, of course, only in the y direction, so we need our y subscript on our acceleration. Our acceleration in the y direction is negative 9.8 meters per second squared. Now, if you had said the displacement is positive, then that indicates that the ball's direction of motion in the y direction is upwards, yeah? Or you're saying that downwards is positive. Then you would need acceleration to be positive as well, okay? That causes problems, though, when you get an initial velocity upwards, and then that would have to be negative, and it starts getting messy. So generally, up is positive, down is negative. Keep that in mind for displacement and acceleration. All right, that's about everything we need. We can now solve this problem. We want to know the impact velocity. So let's start pulling out some formulas, and I encourage you guys to go to that gravity and motion section and have a look at some formulas that have most of the known information in them. What's a useful formula that has most of the known information in it? That first one, we don't have time, so that mostly rules that one out because time's a massive component. The second one, we also don't have time. The third one, are we missing anything from that third one? All right, let's write it down. Vy squared equals 2g sy plus uy squared. That looks like it's going to be a useful formula because we are looking for v, yeah? And we already know vx. What's vx? Well, maybe we take a step back. What's ax? 0. If I am not accelerating in any direction horizontally, what is my final velocity horizontally? my initial velocity horizontally. Yes? Okay, these are the key things we need to recognize. We need to understand that there's a lot more known information here than what the problem gives us, because we're physicists and we understand this problem. We're not accelerating horizontally, so at the start and the end, the amount of energy into our horizontal motion has not changed. We haven't lost velocity in the horizontal. All we've done is gain velocity vertically downwards by accelerating downwards. So our total velocity, our vector, our our resultant vector, thank you, sorry. Our resultant vector is going to be a greater number than our horizontal velocity. Our resultant velocity is going to be quite large because we've accelerated downwards, okay? All right, so knowing this, we can now solve for Vy. Vy is going to equal the square root of all this, except the Uy is going to cancel to 0 immediately because we have Uy is 0. We're left with the square root of 2 times g is just negative 9.8 times sy, which is negative 75. And this is the crux of this negative positive problem. If you solve this with a positive displacement, guess what happens? You get the square root of a negative number. Does anyone know what that is? A complex number, yeah, imaginary numbers. You don't need to do imaginary mathematics in my class, okay? Please don't. In fact, we're going to do, in projection at an angle, we're going to do a problem where you can solve it with quadratic equations. I'm going to tell you to please not solve it with quadratic equations. Okay? You can, but you don't need to. We can figure these things out in different ways. Okay, so that will just become, if we plug that into a calculator. Has someone already beat me to it? Yep, go for it. 7, what? 7 root 3, can you turn it into a surd? Not a, I mean, from a surd into a 38.34? 38.34? Excellent. 38.34. If we just pause for a moment and think about our significant figures here, maybe we leave it at 38. Okay, we'll say 38.34, and then we'll equate that to 38 meters per second. Pardon me. Okay, is that our answer? No? Right, that's Vy. What are we looking for? Find V. Now, from here, if you know what the next step is, you can just go nuts. But I'm going to show you what you're doing here. You have a Vx, and you have a Vy. You have an X and a Y component. We want our resultant vector. V. All right angles, nice right angle triangles. We're doing Pythagoras' theorem. This is Vy as well. So Vx, Vy, V is our hypotenuse. So V squared is Vx squared plus Vy squared. V will equal the square root. Vx was 35 squared. Vy was 38 squared. And you, of course, get the answer 130. No, I don't know. I would come to you, but I'm attached to my computer by a microphone. Is it now? What's the actual time? It's right now. Cool, thank you. Keep this, keep this. They stop you at the gate, you need it. Thank you. Okay, what do we get? Anyone beat me to it? 50, yeah, 51, and we'll round that to 52. We'll say 51.666. No, not the devil's number, not quite. 52. Okay, stop, absorb, ask questions, check logic, Make meaning. Why are you giggling at formulas? Hilarious. Nothing? That was fine. That's okay? Would you think to do those steps yourself? No? Find a way to make sure you would. Yeah? Make meaning from this. Find a logical reason why you would do each step. Why did I use this formula? Why will you use that formula? Because it includes mostly variables we know and the one variable we're trying to find. Very easy to solve. Remember, variables, they could be any number, but if we only have one variable and some numbers, we can always find it. If we have multiple variables, well, it gets a bit messy, but one variable, very easy to solve. Then I just substituted numbers, I found known information, I relayed that back to what the problem's actually asking, and I thought about what that means. This is drawing on our vector analysis that we discussed last lesson. We needed to find a resultant vector. So I did a vector analysis diagram and calculated a resultant vector using Pythagoras. That's fine? I'll leave it up for a little bit longer while I prepare your exercise, and I'll leave you'll get a fair bit of time today to actually just work on this yourself. Let me grab that. Anyone need 10 more seconds with the example? No? Tanika, you good? Yep. Yep. What's that? No, let's do explain whether the horizontal is independent of the vertical component. Don't worry about that. Explain how it can be negative when it gets faster and faster as it falls. Yes, do that. Drop ball and a ball projection. Yep. Yep. The initial and final components of horizontal. Yes. For the record, each of these can be done with one sentence. This one maybe two, but realistically, each of these can be answered in a sentence or two. Okay? 1 to 2 sentences, 1 to 2 sentences, 1 to 2 sentences. Sorry? No, this is Check Your Learning 1.2. 1.2. So if you're following along in your textbook. Page 49. Question 5, definitely worth doing. Question 6, definitely worth doing. All right, let's go. We have a solid 15 minutes for this.